So in this video we're going to look at the vertical circular motion again, which is non-uniform circular motion, but we're going to have an object, say, going around a loop. Okay, so let me redraw the loop here. So it'll be a block, say, going around a loop, and we'll figure out a bunch of things for this situation. So first of all, what we know is that if I have a block of mass m, okay, and as it moves around a loop, okay, so while it's at the bottom of this loop, in fact, I'm just going to get rid of this. I'm going to make this a loop like so that you know it's moving along the circle. So at the bottom of the loop, it's going to have a speed v bottom, okay, and I'm going to move this block a little bit. So at the bottom of the loop, the speed is going to be v bottom, and what we know is that in this case it is the forces that are acting on the object are going to be the force of gravity, which is mg, then the force of tension, and a result of all this is, because if you look at this, it's moving in a circle, so result is going to be the mv bottom square over the radius of the loop. Okay, so clearly you see a similarity between this case and the example before in the previous video, where what we have is that T bottom minus mg is equal to mv bottom, not T, I'm sorry, that should be the contact force. Okay, so it'll be F n, say, bottom, so it'll be Fn at the bottom minus mg equals mv bottom square over the radius. So from here we can figure out, you know, everything we need to for the either the contact force at the bottom or the speed given the contact force and all that. Now on the other hand, if it's at the top, okay, once again we have the contact force pushing it down, so Fn top, okay, we have mg pushing it down, and the result is an mv top square over r. Okay, and what this does is it gives us Fn top plus mg equals mv top square over r, and from here we can figure out once again the contact force at the top, or the tension at the the speed at the top. And if you see, this is completely similar, analogous to the previous problem, which was a mass attached to a string moving in a vertical circle. So there's a repetition of that. The only thing is that the tension in that example is replaced by the contact force in this one. Okay, and once again, you probably guessed the condition for this object to be able to complete the loop. Okay, you probably guess it right by thinking that, hey, for it to just complete the loop, okay, the Fn top equal to 0 to just complete the loop. So we could use this to figure out the minimum speed, and so this is the F top, let's call it minimum, is nothing but square root of g times r. Okay, just like we had square root of g times L for the previous problem. Now complete similar, this problem is no different than the other one. Now we can use this, okay, speed to figure out the minimum speed the object must have at the bottom of the loop, okay, so that it completes the loop. So let's do that. Let's figure out, let's calculate speed at the bottom such that it completes the loop. Okay, now in order to do that, okay, we're going to go back to using energy ideas. So what we have is, we have our loop. Okay, we are going to try to figure out the speed at the bottom. This VB is what we do not know, and but we know what V top is. We know that we wanted to just, so that it just completes the loop. We wanted to just, we want the minimum speed at the bottom such that it just completes the loop. So we know what V top is. V top is equal to square root of g times r for this case. Okay, so we know that. So we can use mechanical energy conservation to figure out the speed at the bottom. So MEI equals MEF. Okay, let's figure this out. So at the bottom, all we have is kinetic energy, which is 1/2 times mvb square. The potential energy is 0 of gravity. At the top, it has both kinetic, which is 1/2 m times square root of gr, the whole thing square, plus it has potential energy, and it is going to be m times g times the height h. If you look at this picture, the height h is nothing but twice the radius, 2 times r. Okay, so once we have this, now we can do the algebra here. We have 1/2 mvb square is equal to 1/2 mgr plus 2 mgr. Now here I can multiply and divide this by 2 so that I have the same denominator, and I get 1/2 mvb square is equal to 1 plus 4, which is 5 mgr over 2. The m's cancel out and the 2's also cancel out, so we end up getting vb equals square root of 5gr. Now understand, this is, once again, this is a minimum speed at the bottom. Okay, this is not the speed at the bottom at all times. It's the minimum speed at the bottom such that it completes the loop. Okay, anything less than this and it will not complete the loop. Anything more than this, it's going to complete the loop without any problems. Okay, so here we've also used energy ideas to calculate the speed at the bottom, and now you probably realize that we can do all these loop-de-loop problems where we can toss something from the top and it can go and go around the loop and do all kinds of stuff.